This is an example of execution trace of a quicksort. So suppose we have a data as follows. Then this one is used as a pivot. So we are going to divide into two by partitioning. So if you do partition, those ones on the left of a pivot, those ones are on the right of a pivot, and then we recursively sort left side first. So in left side first, then 19 becomes a pivot, so left hand side and right hand side is separated by partitioning like that. And then finally we have only one data, so they are just base case of a recursive call. They are sorted, but they are around 19, so we will have this one sorted out. Then right hand side of original array, so this is the one. Pivot is a 33, so we divide into 2, 29 and 35. Each of those have one element, so they are sorted out. Put together, we have this form. Now combine all together around the 26. So you have 26, the one on left hand side is sorted, and then the one on the right hand side is sorted. So we have a combined array as a result of a quicksort. Here, what we need to understand is the choice of a pivot. If the choice of a pivot is very poor, which is not someone in the middle of the array, then sorting algorithm, we don't take any benefit of a recursive design into two halves. So if we have an array there and the pivot, let's assume pivot is always the smallest one. For example, it is already sorted out, something like this one. Then we don't have two partition. Always we will have one partition only. Then the quicksort will run into n squared. But if we choose a pivot approximately in the middle of the array, then it would be n log n. So choice of a pivot is very important, but unless we have sorted data, it's impossible to find the exact middle. If we have already sorted out, then we don't have any need for sorting at all. So it's a contradicting idea. So finding something in the middle very quickly without sorting is something important thing. So there is no guarantee that choice of the pivot would partition the list exactly into two halves. It's no guarantee unless you sort it out. So the choice of the first entry is often poor choice if the list is already sorted and the first key make one of the partition list empty is like that. So to avoid the poor choice case, the data is randomly shuffled at the very beginning once. Then after random shuffle, then perfectly ordered data, they are just completely removed. I mean, it's just randomly shuffled. So by choosing the first one as a pivot is not guaranteed to be in the middle, but it will not be a very extreme case though. So shuffling at the very beginning of a quicksort algorithm is quite important. So here, if I go back to the algorithm sketch, so here quicksort algorithm, before you apply recursive design, do shuffle and then implement a quicksort. Then now we need to do shuffle as quickly as possible. It should not be very time consuming one. The best case quicksort algorithm will be n log n, so the shuffling should be quite fast. So we could implement shuffling in order of n, just linear, just going through the array list once, then it would be shuffled. And that algorithm is explained here. And this is a real code. So given array and the size, how do we quickly shuffle the array? This is just a random number, randomizing the seed It's a randomizing the random number seed so that random function generates a random number. So what you do is as follows. So given array, beginning with the second element, so I is 1, and then through the last element, what you do is generate a random integer between 0 through I. So if I have index 1, then modulo 1 plus 1, 2. Modulo 2 means you can get only 1, 0 or 1 like that. So generate random integer between 0 and I. So we are at I now. Then generate random number and then swap the data with the randomly picked position. And the next I generate random number and then swap this one and the whatever random number is picked as an index and continue to so. At this moment, generate random number 0, 1, 2, 3. If it's a 3, just keep it there. If it's a 1, then swap those two, 0, swap, and the like. So, and then next one, generate random number swap, generate random number swap. By doing so, we just shuffling the data by going through the list on array once. So time complexity of shuffling is big O of n, which is a linear algorithm.